Hi, I'm Emily, one of the 2021 to 2022 Pawsey summer interns. Now, my background is in physics and astronomy, but this Pawsey project was quite different to anything I've done before because instead of looking up at the sky, it focuses on what's below the ground. For the past 12 weeks or so, I've spent some time working on geological models to better understand how and where mineral deposits form beneath the surface of the Earth. During this project, I've worked with 3 supervisors, Dr. Uli Kelker, Dr. Heather Sheldon, and Dr. Thomas Poulet. And I've actually done my entire internship remotely. So we've never met in person, but I've been in constant contact with them all over the course of my project. And apart from working at home instead of in an office, I've really had the full internship experience. I've met all of the other interns for weekly catch-ups and attended the seminars organised by our mentors. So, I've done my work from the east coast of Australia, but I've been using Magnus and the remote visualisation tools on Topaz over at the Pawsey Supercomputing Centre to model a site in the Northern Territory known as the Macarthur Basin. The first thing I focused on was working out how some of these models of the Macarthur Basin scale in terms of memory usage and computing hours when run on a HPC like Magnus. Now, the actual geological modelling in this case is performed by a finite element code called MOOSE, which solves equations on a grid or mesh to produce our models. And after speaking to some of the MOOSE developers on GitHub, we learned that the memory used by these simulations should scale as 3 times the degrees of freedom in the mesh times the size of a double. Now, that is the case when you run the simulation on just one processing core. But Magnus has just under 1,500 nodes, corresponding to almost 36,000 cores. So, to work out how this scales on HPC hardware, I ran the same simulation several times, requesting different numbers of processors. I started out with a coarse mesh, which only uses 10 gigabytes of memory when run on one processor. So it's something you could probably just about manage on a high-end desktop or laptop. But as you can see from a slice through this model, it's so coarse that the element size affects the gradient of the rock, which is definitely not ideal. With this project, we really wanted to see how far we could push these models with the resources available through Pawsey. So my supervisors gave me 2 more meshes of the same Macarthur region, each with many thousands more degrees of freedom, which means they're far too memory hungry to run on a local machine, but they have a much smoother gradient in that same slice of the model. And we see that for all 3, we're using slightly more than the memory estimated from our equation, but also that the real memory usage still scales linearly with the processors used. In fact, I found that for all 3 meshes, the real memory usage is only greater than the predicted usage by a factor of about 1.3. This was a great outcome because we were able to run models that are too memory intensive for anything but a supercomputer like Magnus, and we were able to work out how memory usage scales for these kinds of simulations, which will make it much easier in the future to run these geological models efficiently on HPCs. The second half of my project was focused on visualization. So, for example, I could take the most refined model we had and use a program called ParaView to image it. Again, because even the output of this model was several gigabytes, I had to use Pawsey's remote visualization tools to run ParaView on Topaz, another HPC designed for GPU-intensive tasks. And this allowed me to create visualizations like this, where we can see the full 3D model, picking out interesting properties like the shale content of the basin and where the fluid flows and therefore the minerals are likely to collect using vector fields. At this point, I also started varying some of the physical parameters of the models to see how this would affect fluid flow, which in turn required some more careful visualization in order to work out what changed between the models. So I used something like this. And they're the kinds of things I've worked on over the last couple of months. For someone who had a background in physics and astronomy, this was a really interesting change of pace. I got to learn lots about geophysics and geological modelling, as well as getting to play with high-performance computing resources like Magnus and Topaz. I've learnt a lot from my supervisors, Pawsey mentors, and fellow interns. I know I'll use lots of the skills and knowledge I've gained over the past few weeks in my PhD, and hopefully I've produced some useful work as well.